The universe was really small and dense at one point, and then all of a sudden it wasn't. But wait a minute. Let's rewind and figure out what happened right here. This is because of two things, entropy and dark energy. To put it simply, entropy is the measure of order in the universe. It's a measure of uncertainty or randomness. The higher the entropy, the more disorderly the universe is. It's like your bedroom. A messy room is a high entropy state because it's much harder for you to be certain of where any specific object could be. For example, that sock you lost last week. But once you clean everything up and make it neat and orderly, it's much easier to be certain about where an object will be. This is entropy in a simple nutshell. But why is it important? Simply put, it could be what causes the end of our universe. Before we get to the end of the universe, we need to discuss what events will occur between now and then. This video is much like a sequel to a video I made recently called What Will Happen in 1 Billion Years. If you haven't seen it, I suggest you watch it. If you do, this video will make more sense. Anyway, right now, the Milky Way galaxy and the Andromeda galaxy, the closest galaxy to our own, are racing towards each other at a speed of about 110 kilometers per second. But in 4 billion years, the night sky will look the most beautiful that it has ever been. The collision of galaxies sounds like a really big threat, but actually our solar system will most likely remain intact. Due to the huge sizes of our galaxies, this most likely won't affect anything inside our immediate neighborhood. Andromeda is 260,000 light years across, while the Milky Way is only about 100,000 light years. And I say only 100,000 light years like it's nothing. But at our highest estimate, our solar system is only about 4 light years in diameter at most. When our galaxy collides with Andromeda, the night sky will be filled with gas clouds and nebulas forming new stars. Assuming there's still life on Earth or in our solar system at this point, because galaxies are mostly empty space, we only need to be worried about avoiding any object within light years. Oh, it may be our own sun. In about 5 billion years, the hydrogen in the sun's core will be completely exhausted and will leave what is called the main sequence, a place where dwarf stars who aren't quite giants live. And this is when the sun will begin to expand, which isn't exactly good for any life on Earth. The Earth, Moon, and according to many scientists, maybe even Mars will be swallowed whole by what is now the red giant sun. But there's an upside. This destruction may cause Titan, one of Saturn's moons, to have conditions extremely similar to what Earth's are today, meaning that we could possibly have living conditions on Titan. But even then, things aren't too safe. Because in the year 22 billion, the first universe-ending scenario comes into play. The Big Rip. Low entropy states require work to achieve, so naturally everything, even on the scale of the universe, seems to tend towards disorder. You can tie this in with the Big Bang. The universe was in an extremely low entropy state in the beginning. All the matter and energy in the entire universe today was compacted down into one minuscule point. Since then, the universe has been expanding, cooling down into a higher entropy state, a more disorderly state. You would think that over the billions of years since the universe's beginning, the universe's expansion would slow down, but actually, it's doing quite the opposite. It's speeding up. This is due to dark energy. We have known that the universe's expansion has been speeding up for decades, but the reason why remained unknown. So we call it dark energy. Right now, the idea is that dark energy will continue expanding the space between galaxies, and that large structures in the universe like galaxies, stars, planets, and even molecular bonds will be strong enough to stay held together. This is due to forces such as gravity and the weak and strong nuclear forces. If this is true, then dark energy will never be able to become strong enough to pull these objects apart. However, there is a possibility that it might not work like that, and this is a problem. There is a bit of experimental evidence that suggests dark energy may get even stronger over time. If this is true, then eventually, in billions of years, the distances between objects won't matter. Anything and everything will be torn apart. First, the galaxies themselves will be ripped apart since the space between objects in a galaxy is so massive, like we talked about with Andromeda. Then, the star systems will be torn apart, our solar system. Then, the stars themselves, and then the planets that even inhabited these solar systems. And if dark energy is strong enough, If it keeps getting stronger and stronger over time, then even objects that are held together by stronger forces, molecular bonds that are held together by the strong and weak nuclear forces, will be shredded apart by the now overpowering dark energy. Nuclei themselves will be ripped apart from their atoms, and this will result in a universe with nothing left. Everything has been ripped apart, down to the very last atom. That is the Big Rip. When dark energy causes space itself to expand faster than the elementary particles that make it up, the universe would just be a sea of empty particles that would never be able to interact with anything ever again. But keep in mind, this is theoretical and based off of only a few scientific experiments. So let's say that doesn't happen. What will happen next? Even if the universe isn't violently ripped apart by dark energy, it still exists. Or at least we think it does. And it is still causing the universe to expand. So by the year 100 billion, dark energy will have caused the entire universe to expand so far apart, even at the speed of light, we won't be able to see or interact with any galaxies that aren't a part of our local group. Out of an entire universe made of hundreds of billions of galaxies, in 100 billion years, we will only be able to interact with a measly 54 of them. And when you do the math, it's kinda sad how little of our universe we'll be able to interact with. In 1 trillion years, these galaxies that we call the local group may collide with one another, back to back to back, until eventually the local group is one mega galaxy. And as cool as that sounds, it's kinda lonely in a way. For any life living in the galaxy, that's it. That's all you'll ever know. And around this time, all the gas clouds that are necessary to form new stars and solar systems will begin to exhaust themselves until eventually there are no new stars being born. All the stars that are alive then will be the last of their kind, until the very last star in the universe fades away into nothingness. And eventually, the universe will go dark. Which leads us into our second doomsday event for the universe, the Big Freeze. In 25 trillion years, the last shining star in the universe will either fade out or be swallowed into the supermassive black hole at the center of its galaxy. In 10 to the 30 years, black holes will begin to eat the remaining neutron stars and dwarf stars, while the black holes themselves decay away over trillions of years due to Hawking radiation. In a Google years, that's 10 with 100 zeros after it, a black hole with the size of 20 trillion solar masses, that is a black hole with a mass of over 20 trillion suns, will finally decay completely due to Hawking radiation. And then, there's nothing. In the immense universe over this unreal timescale, there is practically no activity whatsoever. The only activity is random subatomic particles popping into existence for a brief second before they disappear forever like the rest of the universe. That's all there is. The universe has seemed to freeze to a stop. Entropy is at its highest state. The universe is dead. Except, maybe it isn't. In 10 to the 10 to the 10 to the 56 years, which by the way is a number so big that when I sat down and wrote the script for this video, and even now, I couldn't even figure out how to physically write that number down. I tried to figure out a way to put this into scale, but I can't. It's 10 with this many zeros after it, which honestly just makes me more confused. If you were to try and fully write out that number, with all the zeros and everything on one line on a really long piece of paper, that piece of paper would be so large that it wouldn't even be able to fit within our observable universe, due to the sheer length of that number. In that many years, due to those subatomic particles we mentioned, combined with quantum tunneling, a phenomenon where particles seemingly instantly teleport between locations, even faster than the speed of light, there is a chance there could somehow be an extreme random entropy decrease at an extremely specific point in the vastness of the universe, where all subatomic particles in the universe quantum tunnel to the same exact location at the same time. This would result in a new Big Bang, a new universe, or maybe new universes. The behavior of these subatomic particles are quite random and can be quite confusing if you aren't familiar with them. The way they interact with one another doesn't exactly make sense if you're not a quantum physicist. And even then, it's confusing for them.